when the temperature is below the lambda point, it starts dripping off the bottom. It's not easy to make these pictures because this is liquid helium at about 2 degrees absolute, so you have to keep out all of the heat radiation that you can, so you have to filter the light coming in and just use the part which shows the effects. You can see that dripping off the bottom now of the that's the film flow I was talking about. The next one, this experiment, there are 2 columns of helium connected by a super leak below, and what you're watching is just one of the 2 columns, and then the helium can oscillate through the super leak between the 2 columns with very little damping. And what you're looking at is just one of the 2 columns, and you can see the helium moving up and down in the column. So that these are I think we could shut off the film now. Let's see, that seems to be, that one seems to be out of place. This shows that the 2-fluid model applies to superconductivity as well as to liquid helium. The major difference between liquid helium and the superconductivity, electrons and metals, is that the electrons are charged, so that when you get a current flow, you've got an electric current which produces a magnetic field, and the magnetic field in turn affects the motion. The equations for the, in terms of the 2-fluid model, are similar, but the velocity, superfluid velocity, is given by the canonical momentum, which is the one which is related to the wavelength, and the vector potential, which describes the magnetic field. And so that if you have no current flow, Vs is equal to 0, then Ps is related to the vector potential, and this gives a quantization of the flux. One of the properties of a superconductor is that it excludes a magnetic field. If you put a superconducting sphere in a magnetic field and have it above the transition point and cool it below, the flux is pushed out as indicated on the right. And so that's another property of a superconductor, is that not only is the electric field equal to 0, it's a supercurrent, but the magnetic field is equal to 0. Now this shows that if you have a superconducting ring with a supercurrent flowing around a a circular ring, as indicated here. It's the total flux through the ring which is quantized rather than the circulation. And the total flux is a multiple of a small flux unit. The small flux unit is given in terms of the fundamental constant, hc over 2e. It's about 2 times 10 to the minus 7 Gauss per square centimeter. And it's the fact that this is quantized that you can't have any amount of flux, but you have to have, it has to be an integral multiple of a flux unit that prevents a current like this from decaying to zero. In a large superconducting magnet with a field, say, of 40 Tesla or so, there may be 10 to the 15 flux lines or flux quanta in the magnet. But it's the fact that you can't change this large number, 10 to the 15, by 1, which makes the persistent current flow. It's costly in energy to change it by 1 unit, so even changing it by 1 unit in 10 to 15 is enough to prevent the decay of the supercurrent. This shows that the superconducting state is occurs in a region when the temperature is low enough and the magnetic field is low enough. It's superconducting, otherwise it becomes normal. So it's a critical field. And the explanation here, see how the time is going. The explanation here, since electrons are fermions, they obey Fermi Dirac statistics. You can only have one electron in a given, with 1 spin in a given quantum state. Means you can't have macroscopic occupation of electrons, that they obey the wrong sort of statistics. But what happens in a superconductor is that you have a pairing. If you have a normal metal, as indicated here, and this is supposed to be a 3-dimensional diagram, you fill all of the states up to a certain energy level or momentum, as indicated in one of the earlier slides, that in order to occupy all of the electrons required may take a very large number of these states. And so that at thermal energy is only thermal energy is only enough to raise electrons to small energies above what's called the Fermi surface, the highest normally occupied state. And so this shows a typical configuration in an idealized normal metal where the electrons would fill a sphere in momentum space. But what happens is that, as Cooper, Schrieffer, and I have found in developing the theory of superconductivity, is that the superconducting ground state you can think of as made up of many low-lying normal state configurations in which the states are occupied for no current flow of states of opposite spin and momentum. And this would show just a couple of, an idealized way, a typical paired configuration, and you could describe any paired configuration if you give the ones which are occupied and the ones, just the occupied states, and then of course you have to have enough occupied states to accommodate all of the electrons. And so that in the superconductor, made up configurations like this, low-lying configurations, since you don't excite the electrons very far above the Fermi sea to form these configurations, but this shows a typical one. And the ground state wave function is then made up of a linear combination of all of these possible paired states. And so it's a macroscopic occupation of pairs of zero momentum. Each pair has zero momentum, although the electrons are still in individual states. If you have a current flow, the common momentum of the, not necessarily a current flow because of the effect of the magnetic field, because if the canonical momentum P sub s is different from zero, then the pairs have a common momentum, total momentum of the pairs, and you have to have the same momentum in every pair, so you have macroscopic occupation in pairs, and this is essentially the pairing theory of superconductivity. I think that's about the... this just indicates some of the dates discoveries were made. And I think I have another slide. Prior to the development of the microscopic theory in 1957, there are many phenomenological theories, theories which describe the properties of superconductors, some of them very successful, but not understanding what's going on at the microscopic level. And what Cooper and Schrieffer and I did is to describe what's going on at the microscopic level. All I'll say about the new high TC superconductors is that there's strong evidence that it's also pairing there, but what gives rise to the pairing is still an open question. Well, I certainly appreciate the opportunity for being here, and want to thank you very much.